Most people went through and did the first equation. Those are our answers. Okay, how do we come up with those answers? Okay, identifying oxidation states, what do we have to do? How do you identify oxidation states? Okay. Oxidation states are always a solve. Always. Sometimes that solve is trivial. Okay? And this is why things get kind of misleading, is you see the simple examples and just go, oh, the oxidation state is the charge. Okay? This is a common misconception, and not just among students, among faculty. Okay? Oxidation state applies to an atom. Charge applies to any unit. So if I'm going to determine the oxidation state for, say, that first tin on the reactant side, well, there's one tin in that unit. I don't know its oxidation state because Mike said, what did Mike say about oxidation state? You always solve for it. This then equals what? I'll accept +2, but I want something less specific. 0 is now wrong. It's the overall charge. Okay? The overall charge in this particular case happens to be +2. How do I know it's a +2? It's written in the upper right-hand corner. Okay? This is a big kind of departure from what you did in nomenclature. Because in naming, when we balanced out the charge of each of our pieces, okay, and what we called charge, okay, we didn't get a charged overall structure. We always ended with a neutral thing because that's nomenclature. We're trying to make a neutral compound. Here we aren't concerned about what we're making. We're working with what we have. Okay? So the charge can be something other than 0. Okay? And very oftentimes is. So in this case, I now go through and solve. Well, I don't want the 1 on that side, so I'll divide both sides by 1, and I get x equals 2. 2 divided by 1, 2, thank you. I would get +2. What did I say x was? Don't you dare tell me +2. The oxidation state for tin in tin +2. Right? And now I have its oxidation state. I have to go through and do that for every element on both sides of the equation. Right? Once I have all the oxidation states, then I can potentially go through and start to evaluate what was oxidized or reduced. Okay, to do that, I'd have to look at what changed. So tin went from a +2 to a +4. Okay, how does it go from a +2 to a +4? Okay, a loss of electrons. Okay, mathematically, a loss minus sign of a negatively charged species, which equals positive. Did my number get more positive? Yep. What does that mean? That means that species was oxidized. Okay? Not to, complain about different mnemonic devices. Loss, electrons, oxidation. There it is. Okay? What happened to the iron? Okay? To go from a +3 to a +2, its oxidation state was reduced. So I could even ignore the whole electron part because it was reduced, meaning it was reduced. It was reduction. Okay? And I have reduced, that says reduced, okay, which meant gain of electrons. Again, GER. Okay? Kind of makes sense? Did you say no? No, it doesn't make sense? Oh, okay, sorry. I was like, okay, we can do more. It's not a problem. Okay, so there's questions 1 and 2, because we've got our oxidation states, we've identified oxidized and reduced. The next part is the tricky one, our agents. Okay, agents are always tricky. Okay, per the slide, spy versus spy, if you know anything about comics. Okay, we're looking at a spy. Our spy is tricky. Yes, the whole point of a SPY is to work from one side and go destroy the other side without the other side knowing. They are intentionally tricky, so we have to be careful with them. Right? So when we look at a reducing agent causes something to be reduced. Right? So if I'm a reducing agent, I cause you to be reduced. So what does that mean happen to you? You have to gain electrons. Those electrons have to come from somewhere, though. Where did they come from? If I caused you to gain electrons, where did you get the electrons? You got them from me. Okay, you got them from the agent. Okay, well, what happened to me then?
You oxidized.
I was oxidized. Which species was oxidized?
Tin.
Tin. And I now have the reducing agent. Okay? Is that tricky? Yeah. Okay? Remember, it's effectively a SPY. That's the whole point of the agent. That makes it trickier to deal with. Okay? For all of these, what I would argue you should do, if you see a question, identify the oxidizing agent. Okay? Right out of the gate, you know that's tricky. Okay? If I want you to identify the oxidizing agent, so let's go ahead and clear everything. I want you to identify the oxidizing agent in the next question. Okay? So you would see the text oxidizing agent. Okay, which theoretically it'll show here in a second. No, I'm just going to delete all the stuff I wrote. That's okay. Is it actually showing it? Good. Oxidizing agent. So there's the text in black. Okay, because your exam's written black ink, right? Okay. That's no good. You don't want oxidizing agent because you know that's confusing. What happens to the oxidizing agent? Okay. The oxidizing agent was reduced. It's working for the other team. What does reduced mean?
Gain. Everything is opposite.
And this whole everything is opposite. Absolutely. It's freaking confusing. How do we fix that and stop it from being confusing? You write it down. Because the instant it is out of your brain, it's no longer this, well, which one was it? It's now written down. You have something to work with. I know the oxidizing agent was reduced. Can I just look at something and know it was reduced? I probably need to look at oxidation states, right? And look to see how the oxidation states changed. And I could then evaluate how they changed electrons. So ultimately what I'm doing with this work, without even starting the question, I'm converting the question into an easier question for me to answer. I don't want oxidizing agent, I want the species that's reduced. Because that's probably not obvious, I want the one that gains electrons. Okay? If I find the species that gained electrons, what happened to it? It was reduced. If I find the species that was reduced, it was the oxidizing agent. Okay? By writing those steps down as your work for that question, it can simplify your process and it can help you get to an absolute correct answer without getting confused in all the back and forth. Okay? Again, I haven't even started the actual question of determining oxidation states. Okay? Now that I've got an idea of what I'm looking for, now I can go back to my problem and try and solve this out. Okay? If I'm just asked for the oxidizing agent, okay, the species that was reduced, I want to get through this question as fast as possible. Do I need the oxidation state for every single element? No. Why not? So as far as your homework goes, absolutely, you show all the work. Do it all. Okay? But on a test, we aren't expecting you to do everything. We're expecting you to get to the answer. Okay? And we're expecting you to get to the answer in the shortest amount of time. Okay? So what I'm going to do is look at that question and say, is there anything that's easy for me to do? Copper. Okay? Copper is probably pretty easy for me to do. Because copper is by itself in the reactant and by itself in the product. Okay? Which means the oxidation states will become the charges for each of those units. So what was the charge for copper in the reactant? 0, which means its oxidation state is 0. Okay? What is the charge for copper plus 2 in the product? Plus 2, which means its oxidation state is plus 2. Okay? Now I can go through and say, well, what happened to it? To go from a 0 to a plus 2. It lost electrons. Okay? Going to be important here in a second. I heard some extra information being added here. It's not that it just lost electrons, it's that it lost specifically 2 electrons. Okay? Not super important for this, but it helps. Okay? It's just extra information. If it lost electrons, it is... Okay? It was oxidized, ED. It was not oxidizing. Ing is just as bad as the agent. It does the reverse. Okay? So it was oxidized. What was I looking for? I wanted gain of electrons. Is loss of electrons gain of electrons? No. So what does that mean about copper? It's not the answer. Okay, now I have a choice. Okay, NO3 minus or NO2. The agent caused something to happen. If it causes something to happen, is it a reactant or a product? Reactant. It's a reactant. What's my reducing agent? Sorry, oxidizing agent. Nitrate, there's my answer. Didn't have to determine the oxidation state at all for NO3 minus. For nitrogen or oxygen, completely irrelevant. I get to the answer fairly quickly by just looking at the easiest thing to identify. That can get me there. If you don't want to do that, that's fine. You probably have enough time to determine the oxidation state for every single element all the way through. Okay? Kind of makes sense? For the sake of homework, you should be determining the oxidation state for everything. And what you should be getting is something along these lines. Okay? So there are all those answers, all written out. A couple things I want to address within that one. I think I heard a Y. Give me a second. I want to take a look at that red circled species. What is that red circled species? Nitrate. Okay. And when I go through and look at nitrate, I have to determine the oxidation states. How many nitrogens are there? 1. Okay, what is the oxidation state of nitrogen? X. I have to solve for it. Plus 3 oxygens times, okay, Y or -2, depending on your comfort level. Why can we drop in -2 right away? That's one of our rules. Oxygen is always a -2 as far as you're concerned. Okay? This then has to equal what? The overall charge, and the overall charge, as I heard on the left somewhere, is a -1. Now I can go through and solve for the oxidation state. X equals +5. Oh, look at that. My work was right. Make sense? Okay. Which gets us to the other half of this. What is now circled in purple? Nitrogen dioxide. Okay. This is a super common mistake. Most people, or a lot of students, will look at that because you just spent a lot of time memorizing all the nomenclature rules, and you see nitrogen dioxide or you see NO2 and you immediately think nitrite. If it's nitrite, what do I need to see on that?
-1 charge.
I need to see a -1 charge in the upper right-hand corner. I don't have that. Right? That is not nitrite. That is now the covalent compound nitrogen dioxide. Right? Same process, 1 times X plus 2 times -2 equals 0. There's no charge written in the upper right-hand corner. I can go through and solve this, and I get X equals 2 plus 4. Yeah? Okay. There was a what that I thought I heard somewhere over here?
You said 2 plus 4, which might have thrown them off. see it. You can say 2 plus 4. You said x equals 2 plus 4. That's probably not what your mind was doing, but that's
What, for the purple one?
For the
Yeah.
very last thing, you said x equals 2 plus 4. Like I said, that's what came out of your mouth. That's probably not what your mind was doing, but that's what came out of your mouth.
I'll trust you on that. You guys probably listened to more to what I said than what I said. Right. But there was a what or a why earlier than just then. No? So we're good with that? Okay. The next one is even more advanced. Okay. But you should be able to go through and determine all the oxidation states on both sides of the equation and again get to those answers. Questions about anything that's up there? Yes?
So for the reduced part, you only put N, we don't put NO.
So when we're talking about what was oxidized and reduced, we're referring specifically to the element that was oxidized or reduced. Okay? If I'm talking about the agent, notice in the agent here I didn't say N, I said NO3 minus. Okay? The agent is the species that caused it to happen. Nitrogen was in a compound at the time. The species was NO3 minus.
So when we're doing the oxidize and reduce, if we have something like the NO3, do you want us to break it up?
Yes.
So it would be N and N.
Yep. And if we think about, because she just brought up a good point on oxidized and reduced, did anything happen to the oxygen? No. So oxygen wasn't reduced or oxidized. Nitrogen was reduced. Okay? The oxidizing agent is referring to specifically what costume was that species wearing when it did its stuff. Other questions?
How did you get the first part so fast? Like when you just
Which
look
part?
at it and go, okay, it's an oxidizing agent, it was reduced, like.
So how do we jump straight to oxidizing agent or reducing agent and
Right.
all of that?
Because you could clearly see.
The only reason I was able to jump to that is because the answers are right there. Okay.
So you didn't.
So, yeah.
Okay, look at it.
Yeah, I can't just look at these. I will have to write them out. And I mentioned this before, too, on deciding loss of electrons, gain of electrons, and what they mean. When I see that something lost electrons, I don't immediately say oxidation. Okay, you'll almost always either see a pause and maybe even see the eyes roll back in the back of my head because I'm trying to recall information. And ultimately, what am I trying to recall? Leo says Gur. Okay? And that's what I'm pulling up to make sure I can get it right. Because this is ultimately a 50-50 split. It's either oxidized or it's reduced. Okay? And that's one of the things that can be misleading within this entire semester is virtually every question is a 50-50 split. Right? If we string multiple questions together, it's no longer a 50-50 odd of getting it right. It drops pretty drastically. Okay? So just two 50-50 split questions drops your odds of getting it right to 25%. Okay? So you have to be very careful to answer the question specifically and know each of the steps along the way.
Did you look at that third problem?
Because
Not
No.
the NABIO.
yeah, that's what. how do we
Just the
know?
NABIO?
Yeah.
Okay.
Yeah, let's just work out that.
So-
Determining reaction.
The sodium bismuthate is a tricky one to deal with. Why would that be a tricky one to deal with?
Two unknowns.
Okay.
Even after the oxygen.
Sodium and oxygen, or bismuth, are both kind of unknowns even after the oxygen. Okay, what is sodium? That's going to be the next question. What is sodium?
Is it metal?
It is a metal. What is oxygen? What kind of compound do I have? An ionic compound. Because I now know it's an ionic compound, what can I do? Split this into the ions. Where I have sodium ion,
Which is
and then
memorized.
sodium is one you're required to have memorized. You wouldn't have bismuthate memorized, right? Good. Do you know the charge on sodium? Yes. What does that mean you know the charge on? Bismuthate. We now know the bismuthate is a -1 because it has to balance out the sodium. Once we have that charge, now we can go through and solve for the charge on our bismuth.
And so that
Can I?
would be-
Sure. Okay. So this was one of our rules early on that I believe was in the play posit video and not put on here. Once you have an ionic compound, what can you do? Split it into two species, and I get sodium with a +1, and then I get bismuth, and I'm like, I don't know the charge on bismuth or bismuth-8 because I wasn't required to memorize that. But what do I know? I know the charge on sodium, and I know the overall charge on that compound is 0, which means the charge on bismuth-8 must be a -1. What is the oxidation state then for the sodium? A +1. It becomes a trivial solve. For the bismuth-8, there's 1 bismuth times its oxidation state plus 3 oxygens times a -2. This has to equal -1. X minus 6 equals -1. X equals +5. Make sense? All right. That is an admittedly much more challenging one because you aren't familiar with that complex ion. So don't stress per se on that. It just happened to be a random redox reaction I could pull up. Okay? So I'm going to erase all that because we need to get to the next part. And actually I'm going to do it this way.
So if they, like in that compound ion, if there were 2 that we had memorized, there would be no real way for us to figure that out, right?
True. All right. First equation. Is it balanced? All right. This is where we can get a mix of potential answers here depending on your background. When we go through the balance equations, what do we balance? Just balancing an equation. What do you balance? The amount of what? The elements. So I start with tin. How many tins on the left? How many tins on the right? Okay, now I move to iron. How many irons on the left? And on the right? 1. Is it balanced? No.
Why are you confusing me?
Why is it not balanced? As soon as we move into oxidation states, okay, and even single replacements bring this in because single replacements are examples of redox, we have to be cognizant of another thing to balance. That other thing happens to be our charge. What determines charge? Our electrons. Okay? So when we move to the left-hand side of the equation, what is the charge? Okay? We always get some tentative answers here. It's +5. Tin as a +2 is a +2 charge. Iron as a +3 is a +3 charge. So what is the overall charge on the reactant side of the equation? +5. What is the overall charge on the product side of the equation? A +6. Does the charge balance? No. Ultimately what we're saying here, because the charge doesn't balance, is that our electrons don't balance. Electrons are matter. Just like atoms, we have to make sure they balance out. Okay? Because the charge doesn't balance here, our electrons don't balance. What could be an easy addition to this to make sure that charge balanced? Add an electron. Where should I add that electron? Okay, reactant side. So let's add an electron to the reactant side. What's the charge now on the products on the reactant side?
No, we lose an electron.
By adding a negatively charged species to the reactant, what happened to my charge? It went down. It's no longer a +5, it's a +4. Did I get closer or further to balancing my charge? Further. So what does that mean about placing the electron on the reactant side? That was a bad idea. No, wrong button. Okay? So what do we have to do? We put the electron on the product side. Okay? What happens now to the charge? Okay, +5, and then I'd have the +6 minus the 1 charge, and I'd have +5. My charge would be balanced. So now I have a balanced equation. I could say, well, this is good to go.
You can just throw an
Good question. Can I just throw an electron on
It's
it?
not connected.
If an electron is just free floating, okay, it's not connected to anything. That means we have an electron just existing in space. Is that allowed?
No.
Why not? Okay, remember, if electrons are free floating in space, what happens as you walk through space? What might you encounter? You could walk into a random electron, which would then mean an electric shock. Are you getting randomly electrocuted as you walk through space? Different reasons. Okay? So electrons are inherently unstable. We can't balance this out by just throwing an electron in. We have to make sure that the elements balance the charges out on either side. How we go through that process depends on the level of difficulty of the question. Okay? One option is that we never have to worry about it because for whatever reason the question we're given automatically balances out the charge. This is a case where that doesn't happen. Okay? The other method the textbook goes through and explains in section 17.3, which I find confusing as all get out. If you want to read that, by all means go ahead and do so. Okay? 17.4 brings in this new concept of half reactions. Okay? So this was our example. So if we looked at this one up here, we have a redox, right? Zinc goes from a 0 to a +2. Hydrogen goes from a +1 to a... Ooh, then the charge wouldn't balance, right? Look at the charge. Did the charge balance? You say, no, the charge didn't balance. We have to throw in electrons. Before we even deal with electrons, what should we look at? The actual atoms. And when we go through and look at the atoms, what do we notice? I would need 2 hydrogens. Now does the charge balance? Yeah, I didn't have to worry about charge at all. The atoms balanced themselves out and dealt with the charge all in one go. Okay? I don't have to worry about charge. But the other question, it's not as trivial. Sometimes we have to run into problems. Okay? In that circumstance, what we do is split it into half reactions. These half reactions do not exist on their own. We're just looking at half of the reaction and balancing that half reaction as best as possible. Okay? Because I know it does not exist on its own, I can balance with weird things that I'm not typically allowed to balance with, like, begins with an E, electrons. So I can now add electrons to either side of the equation to balance out that half reaction, because I'm making the assumption that in the other half reaction, I'm using electrons to balance it out in a completely opposite location. So the electrons would neutralize each other. Okay? So, what's half the reaction? Okay? Would it make sense for me to balance the reactant half of the reaction? No. Because to balance, I have to balance across something. Okay? I can't balance just the reactants because there's nothing to compare them to. So choosing the reactants doesn't work. Choosing the products doesn't work. Okay? So what do I choose to balance? Half the reaction, or half the reactants and half the product. So I'm going to do tin plus 2, and I'm going to balance that with iron plus 2. Does that make sense? No, why not? They're different elements. Okay? So when I balance my equation, what I'm doing is picking the half that is most similar. I'm going to balance tin plus 2 with tin plus 4.
This is a dumb question. What if you did like a non-metal with a metal or something? Doing that?
More complicated, but it still works. Okay? So there's a reason we're picking a simple example. Okay? So, do the tins balance? How many tins? 1. How many tins? Do the tins balance? Yes. Does the charge balance? No. Okay? This is where I can now go through and balance charge with electrons. And I'm allowed to use electrons now because that equation is never going to happen on its own. So I can use electrons as effectively a placeholder to allow me to figure out how many electrons were transferred. Okay? So how can I add electrons to this to balance that out? Okay. I would add 2 electrons to the product side. Okay. As a nice check, what's the charge on the left-hand side? What's the charge on the right-hand side? +2. Those 2 electrons cancel 2 of the positives. Make sense? So that equation is now a balanced half reaction. What's the other half of my reaction? Iron +3 to iron +2. Is that equation balanced? The elements are balanced. Good specificity. The elements are balanced. Is the charge balanced? What's wrong with specificity? It's a good word. Learn it. Confused. Electrons. How do we balance out the electrons? I need to add an electron to the reactant side. These are 2 equations that run simultaneously, so I can add these 2 equations to each other. Okay? I'm going to say don't write this out. Is it +2? Yeah. So if I just add them up, this is what I would get. Everybody agree with this?
Yes.
Okay. Do I have something that shows up the same on both sides of the equation? Yeah, I have electrons. Okay. So what I can do is simplify. I can gather all of the electrons to one side of the equation. How would I do that? How? Tell me how you would do it. Well, I lied, because you might tell me the right way. Okay. I'm going to gather all of the electrons on the reactant side of the equation. To do so, I'm going to subtract 2 electrons from both sides of the equation. So now on the product side, what happens? 2 minus 2 is 0. On the reactant side, what would I get? -1 electron. Okay. Does it make sense to have a negative species as a reactant? Okay. And not like a negatively charged one, but literally adding less than an existence as a reactant. No, that makes no sense. When we look at our operators, our mathematical operators in our chemical equations, we always use what symbol? A positive. So when I condense these, I'm condensing them by making sure that when I do that condensing of charge, that it entirely balances out and I end up with a positive value. So I'm going to subtract the smaller of the 2, 1 electron from both sides, -1 electron, and I would cancel out the reactant electrons, and I would have +1 electron as a product. Everybody see that? Okay. That's bad, because I have an extra electron. Okay. So we just proved that. That's why I said don't write that. Okay, because all we're doing is showing that that's bad. So somehow or another, we have to make sure that when we mix these 2 reactions with each other, that the electrons cancel out. So that when I subtract electrons, I'm subtracting the same amount from both sides. Which means I have to find the lowest common multiple between the coefficients of my electrons. Fancy terminology of saying how many electrons need to be transferred total in this reaction. 2. Does the top reaction give off 2 electrons? Yes. Does the bottom reaction accept 2? No. That must be 2. How do I make that 1 a 2? Multiply it by 2. If I've multiplied that one by 2, I now have 2 electrons running. Would the rest of my reaction hold true? No. How can I make sure 2 electrons are consumed by iron +3? Also multiply it by 2. And Fe plus 2 by 2. Okay? What about? Yes, I'm listening.
The least common multiple. Does that factor in for the second? Can we figure
What
out?
is the lowest common multiple between 2 and 1? 2. How do I make the 1 a 2? Multiply by 2. How do I make a 2 a 2?
Do you know?
Multiply by 1. Multiply everything by 1. What happened to my coefficients? Nothing. What happens when I now add the equations together? 2 times 1 electron is 2 electrons plus produces Sn plus 4 plus do I have something that shows up the same on both sides of the equation? Yep. What can I do? I can cancel them or attempt to cancel them out, subtract 2 electrons from both sides. The net result is the electrons cancel from my equation. So I'm just going to violently scribble them out. I would erase them, but I want you to see that they're the part of this. Is my equation balanced?
Yes.
If we check tin, how many tins? 1 and 1. How many irons? 2 and 2. What's the charge? So charge is the only one I'll go through and write down. I have a plus 3 from iron. How many plus iron plus 3s do I have?
2.
So what is the charge coming from iron?
Plus 6.
Plus 6. Charge coming from tin?
Plus 2.
Plus 2, which means the total charge there is? 8. On the product side, how many tins do I have? 1, so there's a plus 4. I have a plus 2 coming from the iron, but there's 2 of them, which means iron contributes. What's 4 plus 4?
8.
Does the charge balance?
Yes.
Yes. Okay. What was that? No, you don't want to volunteer it again? That's okay. Right. What we're looking at is balancing half reactions. It's a little bit tricky. It requires a little bit more practice. Ultimately, this is the point of looking at oxidation states. Okay. Does it show up on the exam? Well, some of you should have looked at the practice exam. It is in the practice exam. Where does it show up in the practice exam? Extra credit. Okay. The next sequence of 10 slides is now looking through this stepwise all the way through. Okay? It's valid practice. It can help with looking at oxidation states because it's the application of the oxidation states. Oxidation states have a meaning behind them. We aren't doing it just for the hell of it. Okay? We're looking at how these reactions can balance out. If you choose to not evaluate how to balance a reaction, that's okay. Okay? There's plenty of concepts that we just decide we don't want to do. You just have to acknowledge that you will lose those points. That is perfectly all right. Okay? I did the same thing when I went through and did chemistry as well. I gave up on nomenclature. Okay? I just thought it was stupid to memorize rules. I accept that loss of points, which was 10% of a grade. I lost an A because I didn't study nomenclature. Okay? That's my choice. I'm fine with it. If you're not fine with that, then you should adjust. Some of that comes from knowing how much it shows up. How much did it show up? One place as extra credit. If you decide that it isn't worth that extra credit, then that's fine. That's your choice.
But is it going to be in a chemistry?
Yeah, that's what
No.
I mean. Are you going to have to know it for further on?
No. Well, 151 and 152, yes, and you'll see it again then. And you'll see more rules then too. Okay? So, ultimately what this is a way to look at these equations and decide, does our rule set work? If the rule set doesn't work, what do we need to do? Redefine our rules to help improve our solving process. So when we look at the first equation, we can use our standard balancing process, right? Right? So that rule set worked. When we look at the second example, does that rule set work? No. So we need more rules. Those more rules come up with another method for going through and solving it. Right? In that case, our method failed. Failure is not a problem. Giving up and saying, I don't want to do it anymore, is a problem. Okay? So we come up with a way to adjust and account for that. That's the new method. Do you guys want to try one, or you just want to give up on it? Okay, cool. There you go. Look at that last one. See what you can come up with.
The last one?
Yeah, the last one, because the first two we already did. I lied. Don't do that. Do that one. Sorry. Look at this. You will see an equation very similar to this, except there's a floating G in the middle. And you're like, what the hell does a G mean? Okay. That G, if you change the font to Wingdings 3, becomes an arrow. Okay. Just telling you. Okay. Yes, it is a font. Okay. That's where that arrow is coming from. Because if you don't do that, you end up with a stupid, ugly-looking arrow. I didn't like the stupid, ugly-looking arrow. I mean, there's no way I'm going to draw it, but the ugly arrow is something like this. And I think that just looks dumb. So I tried to come up with a way to get a better arrow. By inspection, which is just doing our atom approach, that we're going to have to split this into half reactions, okay? Or at least it's easier to balance by half reactions. If we added these up, the electrons wouldn't cancel out. So what we said is we need the lowest common multiple between our electrons. So we have 3 electrons versus 2 electrons. What's our lowest common multiple between 2 and 3? 6. How do I make that 3 into a 6? I multiply by 2. If I multiply that by 2, what do I do to the aluminum? Okay. The 2 electrons, how do I make those into 6? Multiply by 3. 3 coppers. 3 copper ions, 3 copper. Okay. Now when we go through and run the math on this, we get 6 electrons plus 2 aluminum plus 3 copper plus 2 goes to, sorry, well, since you started saying 3 copper. 3 copper plus 2 aluminum plus 3 plus 6 electrons. Okay, question?
It just went really fast, but
Oh yeah, it
that
definitely
was
did.
better. Like, that made more sense.
Is that a plus after the 3C?
On the left-hand side,
It's a plus.
yeah. Okay. So now what happens? The electrons would cancel out, and we'd be done. We'd have our balanced equation. Okay.
Would you put the electrons on the same side as you have? You already have a positive charge. Like, could we put the 3 electrons on the 2AL?
Could we put 3 electrons on the aluminum side? Okay. So I'm going to erase some stuff. If I had initially placed my 3 electrons over here, is that equation now balanced? No. That equation is not balanced. On the reactant side, what is my charge? A -3. Each of those electrons contributes a -1 charge. There's 3 of them. That would be a -3. On the product side, what do I have? +3. By placing the electrons on the reactant side for aluminum, we actually make it less balanced than it started. Does that make sense? So deciding where to place the electrons, you should always be able to check. Did your charge balance? If your charge balanced, you placed it right. If your charge becomes less balanced, you placed it wrong, put it to the other side. Okay? You mother! God! So, I'm not writing it all down again. We said 2, 3. 3, 2. Okay, I had the +6 electrons. Stupid buttons. +6 electrons. The electrons would cancel out, so if I asked for the balanced equation would be this guy in the middle here. If I asked for the sum of the coefficients, what would my answer be?
3, 4, 5, 6, 8, 10.
10. I don't include the electrons, because what do the electrons do? Cancel out. So sum of the coefficients would be 10. Fun exam question that really gets at understanding half reactions. How many electrons were transferred?
6.
Okay. So if we look at the multiple choice answers I had 2, 3, 6, 12, and then I couldn't come up with another number. Okay, pineapple, that's not a number. She's shouting pineapples at me. Why 2? How many electrons did we need to balance copper? 2. Why 3? 3 electrons to balance the aluminum. Why 6? That's what we needed to balance copper with the aluminum. Why 12? Because when I add 6 to 6, I get 12. Every single one of those multiple choice answers shows up somehow in the process. All of them involve different levels of understanding, and you could very easily guess the wrong answer. Does that make sense? Okay. You won't see 1, 4, 6, 16 in pineapples. Okay? That's not going to happen. Okay? So you have to understand your process to get to that answer. Does that make sense? Okay. We still got a little bit of time, which gets us to our converting, which is, again, a process. Okay? This is the biggest deal within this section. I know you can do these conversions. Okay? I don't care. Okay? What I want you to do is come up with a process that consistently works. Okay? And by consistently, I mean change the unit system. Every single conversion that you could possibly think of needs to be able to be solved the same way. The instant you come up with a new process means you have to memorize something else. Right? So, what would our work be? Because I can't remember if I asked this. How many feet are in 36 inches? 3. How'd you do that?
Because I memorized 36 or 12 inches in a foot.
Okay. How did you get 3? Right? This is an equality. 36 divided by 12. Does 36 inches divided by 12 equal 3 feet? No.
36 inches divided by 12 inches.
Okay. 36 divided by 12 inches. Does that equal 3 feet? No, that just equals 3. Okay. So you've internalized a process because you're used to doing these conversions. That only works when you understand the unit. If you don't understand the unit, you're dead in the water, and I don't want that. Okay? Your process is saying we started with 36 inches over what? 1. Because if it was some other unit, I would have said 36 inches per that unit. I didn't. I just said 36 inches. Okay? If it was over some other number than 1, then it wouldn't have been 36. Right? So now I want to be able to convert into something. In that process, I'm trying to balance those things out. Inches does not show up in the answer, which means inches needs to show up in the denominator. Right? What do I want the inches to become? Feet. Do I know a conversion factor or a relationship between inches and feet? 12 inches in a foot. Where does the 12 go? No. The 12 goes with the inches. Okay? All right, there was a chorus of people saying on the bottom. Okay? And then the 1 goes with the foot. You're tying the number to the unit, not to its location in the calculation. By tying it to the location in the calculation, you've memorized a formula. We'll be doing lots of conversions. That's a lot of formulas. If you just memorize how you shift the units around, you're golden. Right? We'll pick up there on Thursday. Sorry for running a little late.